Hello, my name is Robert Smith, and I'm with New River Community College, and today we are looking at the relationship between equilibrium constants and cell potential. So, if you're given a problem where you're asked to calculate an equilibrium constant, or you're asked to calculate a temperature and are given an equilibrium constant, or any number of other variables, you can rely on a couple of formulae that will be provided to you on any tests for Gibbs free energy. So we know from the previous chapter that we can calculate the Gibbs free energy as negative times gas constant times the temperature times the natural log of the equilibrium constant. That's at standard state. But we also know from our electrochemistry that our Gibbs free energy at standard state is also equal to this equation, where F is the Faraday constant, N is the number of electrons associated with the reaction, and E cell is just our cell potential. So what you would do with a problem like this is you would either be provided or have to calculate or look up the cell potentials of each of the half reactions. So we have two half reactions. We have zinc solid goes to zinc 2 plus 2 electrons. That's one half reaction, and it's in the oxidative arrangement versus copper 2 plus 2 electrons, which goes to copper solid, and that is in the reductive arrangement. So usually when you're looking up the standard reduction potentials, you'll be looking them up in the, just as it says, as a reduction reaction. So when you look at this, you find that the cathode is the species that is reducing, and the anode is the species that's oxidizing. So your E cell, if you recall, is equal to the cathode minus the anode. So in this case, our cathode is given to us in standard reduction potential as 0.34, and then that's volts, and then minus our anode, which this is the anode, this is the cathode, and our anode, if you look it up in the standard reduction potential table, is negative 0.76 volts. So our cell potential is 1.1 volt. So 0.34 minus negative 0.76. So 0.34 plus 0.76 gives us 1.1. Okay, so that's the first component. And then what we can do is, because these two equations here are both equaling our Gibbs free energy change at standard state, we can set them equal to each other. So negative RT natural log of K is equal to negative NFE. And if we're trying to find K, we would divide both sides by negative RT, and that gets us the natural log of K is equal to positive, because the two negatives cancel, so it would be positive N E cell times F over RT. Now I'm putting F over RT in a separate spot because if you are dealing with this at 293K, which we are, then, and because this is dealing with species at equilibrium, and you have to look up the E cell, it has to be at 293K. So we can treat this whole thing in parentheses as a constant. So we can rewrite this as N E cell over 0.0257 volts. Okay. So we can reorganize this equation to be K is equal to E to the Ne cell over 0.0257 volts, which is going to give us volts over volts, which is great because we want a unitless or dimensionless number in our exponent. And we just have to identify what N is. And we do that simply by looking at our anode and cathode reactions. N is the number of moles of electrons. So we have 2 moles of electrons on either side, so we don't need to change anything. If there were different numbers, you would have to multiply the equations by the appropriate factor to get them to equal each other. So you're trying to find them at where they're equal number of moles of electrons. So be aware of that as you proceed. So we just plug this in and we get E is equal to 2 times 1.1 volts all over 0.0257 volts, which if you run that into your calculator or however you'd like to do it, gives us 1.5 times 10 to the 37th power. And that's our equilibrium constant. So it's relatively straightforward. You may just want to recall that K is, you can solve for K in this fashion here. And you can also rearrange it to solve for your E cell just as easily. All you would do is make it so that it's N divided by the, you'd have to flip it so that it would become 0.257 volts over, and then the thing that it would be over would be the N, and the natural log of K would be on the numerator, and then E cell would be also in your on the other side. So you can rearrange this formula however you see fit to solve for the term that you're looking for. Just follow the normal rules of algebra.